Hey guys, I was thinking about our conversation today about showing that functions are inverses and why you have to show both f of g of x and g of f of x are equal to x. And then something I said where if you found the inverse of one, you didn't have to show that the inverse, you didn't have to do that for both of them and show that they were equal to each other. Well, I was wrong about that, and so I wanted to go through an example that I think is a good example that you could use to show kids. So very often kids will think that these two functions are inverses of each other, and they're really not. And there's lots of ways you can show that. One of the ways you can show that is simply by graphing the square root function and graphing the quadratic function and showing that, oh yeah, the quadratic function is not one-to-one, so its inverse is not a function. Or if you were to reflect one or the other over the line y is equal to x, you're not going to get the other one. So that's one way you can show it. But here's where I think showing that you have to show both f of g of x and g of f of x give you x is important. So if we take f of, let's do g of f of x first. So let's say we take g of f of x, we get the square root of x, and we square that. All right, so if you think about putting any number in there, first of all, you're restricted to only numbers greater than or equal to 0. So you take their square root, you're going to get another number greater than or equal to 0, and you square that. So basically, if you think about it, if you can only put x values that are greater than or equal to 0 in, you're only going to get x values greater than or equal to 0 out. So this will turn out to be x, and that's fine. But if you find f of g of x and you take the square root of x squared, well, you can plug any number you want in, any real number you want in for x. Once you square it, it's positive, and then you're allowed to, or 0, and you're allowed to take the square root of that. But if you plug a negative number in for x, you square it, it's positive, then you take the square root, it's going to be the opposite of what you originally put in. So this is technically the absolute value of x, and that's why you have to show that both f of g of x and g of f of x give you x, and that these two are not inverses of each other. And if you want to take it one step further, you could say that we go back to the original, f of x is equal to the square root of x, and g of x is equal to x squared. Well, the typical way to solve for the inverse is switch x and y and solve for y. So we would write x is equal to the square root of y and solve that by squaring both sides. And if we squared both sides, we would get y is equal to x squared. However, if we were to do that for g of x, we would get, start out with x is equal to y squared, and when we solve that, we would get y is equal to plus or minus the square root of x. And that's where on the graph, you're missing that minus square root of x part up there. So you do technically have to show algebraically, if you're going to solve for the inverse, that if you solve one for the inverse, you get the other, and vice versa. And then yet another great way to show this graphically is if you put in your calculator the two compositions, so the square root of x squared and the square root of x, and then you square it, and then put your calculator in sequential mode where it graphs one function and then the next. Check this out. So you saw the first function gave you the absolute value of x, and then the second function gave you y is equal to x for only positive values of x greater than or equal to 0. So I wanted to clarify that because I was thinking about it afterward, and I realized I said something wrong, and I don't want anybody telling their kids wrong stuff because of me.